All right, so our last exception to the octet rule is the hypervalent atoms, and so this is greater than 8 valence electrons. And the second group cannot do this, so n equals 2 cannot do this. So you think n equals 2, again, that's carbon, nitrogen, oxygen, and fluorine. They cannot break the octet rule. Anything below that, so n3 or more, is capable of doing this. And the reason for this is that these molecules are simply bigger. And so there's more room for stuff to kind of fit in without it repelling each other. So think about if you kind of have, positive charges really close to each other, which would be something like this, n equals 2. That would be very high in energy and very hard to maintain. While if you have something more similar to this, right, 3 kind of big atoms, that's more okay. And so think about kind of nitrate as well. You may be tempted to draw this structure for nitrate because it minimizes the formal charge on nitrogen, but you cannot do that because nitrogen cannot break the octet rule. So be careful with nitrate especially. So let's take a look at an example, H2SO4. And so sulfur is indeed capable of breaking the octet rule. But in general, you only want to break the octet rule if you have to. So let's put our least electronegative non-hydrogen atom in the center. So that's sulfur surrounded by these oxygens. And then we remember that OH is a common motif. And so these are going to kind of stick together like that. A lot of this just comes from practice. Think about the valence electrons here. There's 32 valence electrons. We made, let's see, 1, 2, 3, 4, 5, 6 bonds. That's 12 electrons. So there's only 20 valence electrons left. And so then this oxygen needs 6. This oxygen needs 6. And then these two oxygens need 4 each. So that's 0 valence electrons left. And now let's think about our structure here. The octet rule is satisfied, right? Everything has an octet, and hydrogen, like it wants to, has a duet. But let's think about formal charges. So go ahead, pause the video, and take a second to think about the formal charges in all of these. Cool, so what should end up is this oxygen is negatively charged, so is this one, and then this sulfur has a +2 formal charge. So remember, with formal charges, we want to minimize them as much as possible. Since sulfur is capable of breaking the octet rule, we're going to go ahead and do that. So we're going to push these electrons here, that'll get it to a sulfur +1, and then we're going to push these electrons down here, and that'll get it to a sulfur 0, right? So what you end up with is this. And if you think about the formal charge, they are all 0. And so this one is indeed better. And it's okay that sulfur breaks the octet rule because it is allowed to. And it still makes sense. Sulfur has 6 bonds. In this structure, its oxidation state would be 6. And if you think about sulfur, if it loses all 6 valence electrons, it then still has this filled valence shell. So it's still kind of obeying the, filled valence shell rule. Just some more examples, ASF5, arsenic, pentafluoride, right? You can see arsenic has 5 valence electrons, so it could lose all 5 of them to make, or to still have a filled kind of octet. And so it's allowed to break the octet rule. So the correct Lewis structure for this one is like so. Another common example is XEF2, right? Xenon is below period 2, so it can break the octet rule. It's also a noble gas, which generally aren't reactive, but in this case actually are, which is kind of cool. So valence electrons here, we've got, see, 8 from the xenon, 7 each for the fluorine. That's 22 valence electrons. We go ahead and use up 4 of them for these bonds here. And then we give each of these fluorines an octet. So we're left with 6 valence electrons. So we got nothing else to do. Remember, fluorine cannot break the octet rule. So our xenon must have 3 lone pairs and is indeed breaking the octet rule. So again, a lot of this is just kind of practice, practice, practice. You'll see some kind of hints and similarities within the problems.